this a good level? Louder? Good? Better? Okay. I'll move it just a little bit in this direction. And I want this, to the extent possible, to be interactive. So if you have a question, you're probably not the only one with that question. So raise your hand. I may not get to you immediately, but I'll get to you, and I'll try and answer your question. And we can see if we can all get a little better understanding and facilitate the communications that way. I came here to talk about extrasolar planets and planet formation. But then I found out about the diverse backgrounds of the students here. And even though we know more than 99% of the planets we know of orbit outside of our solar system, we know so much more about the planets within our solar system and the smaller bodies within our solar system. This actually informs us greatly about extrasolar planets and what we think they're made of, because we have very limited data there, and also about planet formation. And therefore, I'm going to begin with a little bit of a tour of our own solar system. And with our solar system, NASA and ESA and Japanese Space Agency and the Soviet Union, when it was around, have sent back some wonderful images. There are a few nice telescopic images from the ground. But if we could have the lights dimmed, especially up front and this. Very good, thank you, Isa. I think that makes it a little bit crisper. Now, these,
one on the laptop, sitting.
The one on the laptop, okay. And this is the pointer, if I recall correctly. Okay. Now, these are roughly images to scale. I'm going to have better ones of the planets in our solar system. Close-up of Saturn. A close-up of outer area in the rings and little moons. A comet right after it had been hit by an American spacecraft. Intentionally, there were two parts of the spacecraft. One to hit the comet and eject material, the other to photograph it and study it. And this is a theoretical model representing planet formation in a disk. And this is a painting. And we have things like this is pretty much real color. This monochrome. Now this is artificial, and it's very artificial. Out farther from the star, it's cold. Now, if you studied astronomy, physics, you know that blue stars are the hottest stars, shortest wavelength, highest energy. But we think of blue as cold, you get blue. And this is kind of artistic license. And you have various levels of reality in the images you're going to see. This is really extreme because it's art. But it still is scientific in the sense of the models based. It's more scientific. The art I'm going to be showing is more scientific than most space art. But nice and warm and toasty. If in the actual colors, This may be somewhat realistic in colors. It's probably a lot hazier. But then it just gets dark, brown, dull. People wouldn't like to see it. And all these things, well, there probably aren't much things like that either. But they kind of convey motion, and it is moving around. Again, art. When you look at pictures, this is pretty much true color. This, I think, is more ultraviolet aurora, so it's represented as a violet type color. This is very enhanced color. And most of the color images you see are either enhanced color or artificial color, where color is being used to represent things. My presentations this week, I have 4 lectures and I have 4 topics. But that doesn't mean I'm necessarily going to give the boundaries of one topic per lecture. The solar system, I'm going to go to a little briefer review. So I'm hoping, we'll see, that I can actually get into planet formation next. This was what I planned to do when I came here. But I talked with David, and he's going to be talking about planet formation things tomorrow. So I'm going to give my introduction to planet formation before that, because it's mostly the solar system that's our clues. And then I'll talk on Wednesday about extrasolar planets and wrap up with NASA's Kepler mission on Friday. Even though I think of myself as a theorist, and I really like theory, what we know about the solar system is based on observations and theoretical developments to fit those observations. Now, there are various properties of planets we observe. The most fundamental things that were observed back to the ancient Greeks, but really back farther, is the orbit. Planets. The word is from Greek for wanderers, wandering stars, because they moved relative to the fixed stars in the night sky. And these were studied greatly by Newton and Laplace, various others, and illuminated a lot of physics through them. Kepler was one of these people. That's why we named our mission after him. So the path it travels, then how big it is, and how much material. Very fundamental. Mass, and also, in some cases, in the solar system, we can measure how concentrated that mass is to the center of a body. And I'll discuss that a little more later on. The size, how big it is. If you know the size and the mass, you have the density, and you can get an idea of the composition, what it's made of. And if it's big for its mass, it's got to be made of light things, and that means it's got to have a lot of hydrogen and helium and maybe a few other things, but a large amount of hydrogen because it is the least dense, the lightest element. Now, if something is dense, like Earth, can make it from rocks and iron. You could also, in principle, make something of the same size and density by lead and water. But they're just not very common. Lead is not that common. How are you going to get the lead without getting all the other rocks? And that lowers the density. And then if it's something that's like a mixture of rock and other things that condense at hot temperatures, it better be rock. It's that density. So some things we can get from basic physics, some things we can get from understanding reasonable properties in the cosmos. But then if we see something that's less dense than rock, but too dense to be gas, something intermediate. It could be something intermediate in intrinsic density, like very water-rich. But it could also be a mixture of gas, light gases, and rock. So it gets a little bit tricky there. You observe the spin. If you see markings on the surface or in the atmosphere moving around, you get the rate at which it moves around and the direction. If you have resolved images, you can get the shape of the body. Here we have Phobos and the limb of Mars. Now, Mars is nice and spherical, a few little bumps called mountains, and some of them are pretty big by Earth standards. But Phobos is very irregular. Now, the astronomers know about this, but do any of the biologists know why Phobos would be so irregular? And okay. Well, what's making Mars into a sphere? Everything is being pulled towards the center, the gravity. But Phobos has much less gravity. It's basically just a big rock. And so there's less pulling it in. But the strength is a material property. It doesn't depend on the size. So there's less size, so less gravity, but still the same amount of strength. So that's why small bodies tend to be less regular in shape. There's the temperature, how hot it is, and if you're actually there, you can measure it with a thermometer. But if you're not there, you can get the spectrum of radiation that's being emitted from the surface. And also you can estimate it just by how far it is from a source of heat, like a star. Magnetic field, you can get that from, if you're there, or at a distance. Jupiter's magnetic field was known long before any spacecraft reached there, because there were charged particles which had motion governed by that field, and they radiated in this particular manner, which gave clues to that. If it has a surface, the structure and composition, there are craters on Venus. If it has an atmosphere, also the structure and composition. This is Jupiter, and Jupiter actually is about this colorful. Great red spot. Just to give you an idea of scale, this is the shadow cast by Jupiter's moon Europa, which is only slightly smaller than Earth's moon. You could fit 2 to 3 Earths side by side in the great red spot. Now that really indicates that giant planets really are giant. And I like this pseudo 3D image because it really shows just how much bigger Jupiter and Saturn are than the terrestrial planets. And it also shows that really there are not just 2 types of planets, there are 3. They're the terrestrial planets, the rocky planets, they're the gas giants, which are dominated in both mass and volume by hydrogen and helium, the 2 lightest and most common elements in the universe. but elements that condense only at very, very low temperatures. And then you have these two intermediate bodies, which are called the ice giants, because models suggest they probably have a substantial amount of water and other astrophysical ices like methane and ammonia. But they're not actually in solid form. It's in fluid form. It's far too hot. Plus, we really don't know how much ice there is, how much astrophysical ice, and how much hydrogen, helium, and rock there are. There's certainly a substantial fraction of their volume is hydrogen, helium, but the hydrogen and helium only make up about 10 to 20% of their mass. We think that the rest of the mass is probably a little more ices than rock, but we really don't have good models. We do have much more information than exoplanets, though, because we can get not just the mass, but we have an idea of how the mass is distributed within these planets. And we have that from gravitational data on the orbits of the moons and of the Voyager 2 spacecraft, which went by each of these planets in the latter part of the 1980s. And if you have a body which is spherically symmetric, its gravity outside of it, the gravitational field it creates, is identical to a point mass. Newton figured this out. It took him a couple decades. He invented calculus to do this. It took him a long time from when he realized the inverse r squared and universal gravitation till he published it, because his theory was from a point, and he invented multivariate calculus in order to show that the gravity field of a spherically symmetric body is identical to a point mass at the same position and same mass. So if you're problems with some aspects of multivariate calculus, blame its gravity and Newton's theory and everything. But it only applies to spherically symmetric bodies. And if you have a distribution, even if it's symmetric around an axis, if it's a flattened distribution like a pancake, the gravitational field is different from that of a point mass. And it causes orbits not to be closed ellipses, but to be precessing ellipses. And the magnitude of the precession depends on how non-spherical the distribution of mass is. We see the rotation rates of these planets, and we can measure the non-spherical distribution of mass. But if it were, say, light gases and then just rocky stuff at the center, a lot of the mass would be right at the center, and you'd have almost spherically symmetric gravity. But since these orbits are not Keplerian, they're perturbed significantly, that means the material's spread out. And the models, just to fit that and the density of these planets, say no rock, just ice and a little bit of gas on top. However, we don't understand how you could make a planet with ice without rock. You make a planet with rock without ice because it was too hot for the ice to condense. You can make a planet that's mostly gas because most of the material in the universe is gas. But mostly ice without much of other things, that we don't understand. It's possible that the rock didn't all fall to the center, and it's mixed with the ice and maybe some gas because it's under very high pressures. It's a very complicated physical problem. Back to that when we talk about planet formation. This presents another view of the planets, and it also, there are really just two groupings. They're the inner planets, close in, and then you just see Jupiter and Saturn. You only see parts of their orbit here. This is the asteroid belt in between, but much less mass than any of the planets in the asteroid belt. All the asteroids put together. This is the outer planets. You see the inner planets in there, too small to label. Pluto out here on an irregular orbit, much more inclined and eccentric than the large bodies which we consider to be planets. Now I'm going to give you a little bit of a tour with some close-up images. This Mariner 10, that's a US spacecraft that went by Mercury 3 times in 1974 and 75. And I remember when this was about all you had for images of Mercury. And it looks sort of like the moon. Cratered, airless. It's not that much bigger than the moon. Actually, the way you can tell, the moon has 2 different types of areas. The Maria, dark lowlands, which don't have that many craters, and the brighter highlands. Plus, if you look at the actual craters themselves, because Mercury is more massive and it's also denser because it's much more iron-rich than our moon. Gravity, surface gravity is significantly stronger, and the craters are flatter for a given size. Now, we have messenger images. Messengers been in orbit around Mercury for several years. And this is one of these enhanced color. It's a close-up. If you looked at it with your eyes, you barely discern any color. But this is not artificial color in the sense that this is, it just is an exaggeration of the actual small color differences that exist. And these are based on little differences in composition. This is probably a volcanic feature from a long, long time ago. But the surface, just like the moon, is dominated by craters. Moving out, Venus, nearly a twin of Earth in terms of its mass and radius and bulk composition, but the atmosphere is almost 100 times as dense, a lot more carbon dioxide. Carbon dioxide is a gas that's transparent to visible radiation from the sun, so the energy from the sun gets in. It's not transparent, it scatters back downwards. Longer wavelength radiation that's radiated from the planet upward, therefore it traps gas, greenhouse effect. As we're burning fossil fuels in the forest, we're increasing our carbon dioxide in the atmosphere, and it's It's nowhere near as hot as Venus, fortunately, but we're going in that direction. This is actually over 90 bars, over 90 times the atmosphere, whole atmosphere of Earth in carbon dioxide alone. We have carbon dioxide that's increasing, but it's still only about 400 parts per million. Well, these are cloud features seen in ultraviolet light, extreme violet, taken when the Galileo spacecraft went by there for part of its gravitational assist in getting to Jupiter. It actually has a lot of sulfuric acid clouds, very thick. You can't see the surface invisible, but you can penetrate the surface. It's the Magellan spacecraft, coincidentally, which was in orbit around Venus. Coincidentally, those were both from the early 1990s. And when you penetrate through the clouds, you do see some of these craters. Venus not having oceans, even though it has a thick atmosphere, it doesn't have the same weathering rate. It doesn't have the same crustal recycling rate, so its crust is older, and you can see these older features which have built up over time. There have been more time for more impacts, but no small impacts, because small bodies hitting the atmosphere just burn up. Moving outward, well, you're familiar with this planet. Most of you were born here. This is our moon. And great pictures. And a pretty good view of it yesterday evening. If it clears up, we'll have even better view to this evening, but don't count on it. And Maria Islands. Now, craters. This is the crater you can see up close without having to go to the moon. And I wouldn't say it's worth flying to Arizona to see this. On the other hand, if you're in the area, it's kind of interesting. And it's about 1 kilometer in size. It was an iron body. There are fragments of it about, 20,000 years ago or something like that. And since Arizona is very dry, that's why it's pretty well preserved. Bodies hit Earth. This guy, the asteroid Eros, which is not that different in size from Phobos, and also quite irregularly shaped. It's called a near-Earth asteroid. Fortunately, it's not that near Earth, because this guy is big. This guy's kind of the size, the one that hit, was made it real bad for the dinosaurs. It's the largest near-Earth asteroid. It comes in, I think its orbit comes in a little closer than Mars, so in principle, it could have a bad close approach with Mars and perturb it into Earth crossing at some point. But very cratered, very irregular in shape. It's a little bit smooth in places because material still gets knocked up from little impacts and falls in other places. Moving outward, Mars, and Mars has some real big volcanoes. Even though it's a smaller planet, it actually has mountains that are bigger than Earth. And actually, that's not a coincidence. Smaller planet, less gravity. So it squishes the mountain, and rock has a certain strength, so you can build up to a certain height before it starts pressing down, especially on a planet like Earth where it gets soft. The mantle is something that on short time scales behaves like a solid, but on longer time scales is very fluid. So if you put a lot of pressure on it, it's just going to descend. This is Valles Marineris, the Grand Canyon of Mars. And just like Mars's mountains dwarf the mountains on Earth, this dwarfs what Americans call the Grand Canyon, the Colorado River, which is biggest also in Arizona, also worth going to because it's a lot closer than Valles Marineris on Mars. And it's also a very different type formation because this is a tectonic feature, and the Grand Canyon in Arizona is cut by erosion of flowing water. This is a true color, supposedly. I mean, don't trust the computer and the projector, but fairly true color image on the surface of Mars, taken probably the better part of a decade ago by Mars exploration rover Spirit. This lasted for about 6 years, 7 years. The other twin Opportunity is still going. It's close up. Mars is red, and it's basically just rusty. Iron oxides. It has a thin atmosphere, so it has some more jagged things, and it hasn't rained significantly on Mars for billions of years. So there's not a lot of erosion, things that tend to make rocks rounder on Earth. This is the twin Opportunity, and it went, surveyed Victoria Crater, among other things. Now, moving farther out to the main asteroid belt, this is not one of the bigger asteroids, but it's still a lot bigger than Eros. You would definitely not want to be on this planet when this body this size hit. Fortunately, that hasn't happened in probably over 3 billion years. This is its moon. Still small enough that gravity cannot mold it into a round shape. We do have samples to help us understand what's going on there. This is a wonderful meteorite collection. If you're in New York at the American Museum of Natural History, you go to the American Museum of Natural History, see the meteorite collection. You can see meteorites like this, iron. These are fairly common. This is where it's a fall, which means it was observed to fall. And it's named after the region in which it was found. And this is the type. It's an iron, and there are various types of iron. This is the reason you go to the American Museum of Natural History. This is the size of a car and much denser, over 30 tons, mostly iron. This was brought from Greenland to the United States at the end of the 19th century by the polar explorer Peary, who claims to have been the first to make it to the North Pole on a later expedition. It was an amazing feat at the time, because this is extremely heavy body. If you look at the markings on it, it actually has a lot of little dents, and that's because the Inuit in that area used it for metal for centuries. And the only reason they were willing to show it to the Europeans is the Europeans traded all these manufactured knives and things like that, so they didn't need this anymore. Okay, we'll show it to the foreigners. The more common meteorites, the more interesting ones, things like this one, the Allende meteorite. This was also found in 1969. It was found in Mexico. It's a primitive meteorite, so very interesting chemical composition. And finding in 1969 meant that, this was early 1969, fell down, pieces were collected. They were brought back to labs, which NASA had funded with a great deal of money, preparing to study moon rocks, and this was samples. So a lot of what we know about the chemical composition of the disk out of which planets form, which I'm going to be talking about in my next lecture, is from studying this meteorite in particular, not just this sample, because there were many pieces of it. Okay, let's go beyond the asteroid belt and samples of the asteroid belt to the outer solar system. Nicer picture of Jupiter now. And this has two of its moons, Io and Europa. For scale, Io is slightly bigger than our moon. Europa is slightly smaller. And again, you get 2 to 3 Earths side by side with a great red spot, which is a giant cyclone, giant storm on the planet. These motions persist for long times. This great red spot has been around for centuries, although its shape and color gradually change over time. Io is a very interesting body. Let's go close up on the 4 satellites, 4 large satellites of Jupiter, often known as the Galilean satellites, because they were discovered by Galileo and somebody else, Marius, around the same time. Also seen independently by eye, not with the first telescopes, but by eye from observers in China. But Galileo publicized it by far the best. And there were independent discoveries. These two are bigger. They're less dense. They're about the same amount of rock as these guys, but they're a lot more ice. Europa is actually a fairly pure ice surface, but its density implies that it's mostly rock. And then there's a little layer of ice on top. And when the Voyager spacecraft went by, 2 Voyagers went by in 1979, they observed volcanism on Io. And this is due to tidal heating, immense tidal heating driving volcanoes. And this is because Io's in a slightly eccentric orbit, brings it a little closer, a little farther from Jupiter. Now, tides stretch out a bit, just like tides stretch out the ocean as a result of the pull of our moon and the sun, but Io is close to Jupiter, which is a huge body. So these tides stretch it, and it goes a little closer and a little farther. Well, it goes a little closer, the tides are a little stronger. A little farther, the tides are a little weaker. So it gets stretched more and less. And just like if you have a ball of putty in your hands, and you deform it back and forth, move it back and forth, that heats it up. That's what's heating Io up. And it's heating the surface up substantially and causing volcanoes to spew out material. Now, Europa is a little farther away, but it's also driven to high eccentricity by interactions with Io and Jupiter and Ganymede. And this causes them heating too below the surface. And Europa is thought, based on this theory plus the fact that it has a very smooth surface, which indicates, well, first of all, its spectrum is water ice. It's smooth, which means a lot of melting. And then, from various aspects of the gravity and magnetic field around, strongly suggests that there's water below the surface. In fact, an ocean that's bigger, more water than in all of Earth's oceans. And this is probably an environment that's considered likely to be habitable. Doesn't mean it's inhabited, but there are probably some microbes on Earth where if you put them there, they would survive and reproduce. There's not a lot of source of energy well below the surface, so you couldn't have a lot of photosynthesis, but could have a very primitive biosphere in principle. And maybe even in little areas of kind of wet ice below the surface of Callisto and Ganymede. It's very cold, like 100 degrees Kelvin on the surface areas, so that's not going to be any good. 100 degrees Kelvin minus 170 centigrade Celsius. Might think it's chilly in this room. No. Even Mars, it's warm compared to that. Saturn. Hubble Space Telescope pictures as Saturn moved around, the seasons changed, the projection changes. Some storms on Saturn. Cassini images, close up. Some more Hubble images when the rings were nearly edge-on and Titan's orbit was nearly edge-on. Titan is Saturn's large moon, and Titan, even though it's very cold and very dissimilar in terms of composition to Earth, has some real similarities to Earth. This is Titan, and this is its shadow. So about as big as those large moons. So Titan, I'll get back to it, I'll show you some close-ups in a minute, shows evidence of liquids on it. Now, under the surface, there's a much smaller moon, Enceladus, which has geysers coming up. And it also has liquid water under its surface, like Europa, which could be a habitat, although the environment is such that it would be less likely on this much smaller body that it would have. These aren't necessarily all the time. It may freeze episodically, not sure. And there's less area, less potential for formation of life. Close up, some of these regions clearly melting, not cratering in those regions of Enceladus have sculpted the surface. And here are some plumes. So very contrast enhanced. This part is in shadow, and just a crescent which is very bright, right near the edge, and then the plumes from scattered sunlight. And this is totally colored enhanced to show just the level of contrast there. Titan. This is what it looks like invisible. Pretty boring because it's hazy. You think it's hazy on smoggy days in cities? Well, Titan's even hazier, although it's because there's a much larger area, much larger thickness of the atmosphere and the photochemistry in the atmosphere. Methane is the second most common gas, and the sunlight interacts with that and produces the haze. But the haze particles are small, so if you look at it close up in the infrared, you can see some features on the surface. If you penetrate radar, you can also see features. Europeans sent a probe down to the surface, and this is a view. As it was coming down, it saw some signs of rivers, or at least river beds, things that were cut by rivers, and this was liquid methane or ethane rain, not water. It's much too cold. Water's a really solid rock. This is about 94 or so Kelvin, really cold. Now, you see this footprint. Well, no. There's no sign. That's not from Titan, but it is from someplace other than the world. This is an astronaut's boot print, Apollo astronaut on the moon. Just for scale, because that's kind of the perspective. seen in this image. This was probably taken by the other astronaut who left the boot print, and this was taken by the Huygens probe, which is the European contribution to the Cassini mission, primary European contribution. This is what Uranus and Neptune tend to look like in natural color. But you enhance slight color differences and you see that there are very subtle variations that you can magnify and show real differences in composition. Two bodies are very similar in size, very similar in mass. This is a close-up of Voyager. Voyager also got close-up pictures of Uranus, but they tended to be fairly featureless. That was a quarter century ago, and as the seasons have changed on Uranus, its year is 84 Earth's years, so it's been a little over a season since the 1986 encounter with Voyager. It's gone in a different position. The weather's been different. There's more clouds there, more like Neptune. Uranus doesn't have any big moons. Neptune has one big moon, Triton, and this has geysers too, but they're this even lower temperature. It's like 40 Kelvin, nitrogen dominated, but still the surface clearly has some things that have melted at those temperatures. Now, given the picture tour of the planets, you may wonder about this guy. Well, I'm not going to forget it. We have a Hubble picture of Pluto and its largest moon, Charon. And a year from now, I would be able to show some nice pictures from New Horizons of Pluto and Charon. But we didn't. Pluto got reclassified as a Kuiper Belt object. It didn't get blown up. That rumor was not true. And the spacecraft is still on the way there, so we're going to get some real nice data. So speaking of the controversy of what's a planet, some people said, well, it should be a definition based on just roundness. Now you have some bodies which are clearly round, some that aren't. There's this kind of gray area in terms of size when it's big enough to be round. So it doesn't go just from oblong to round. It becomes less round as it gets smaller. Just like Mars is less round than Earth. It has it's a smaller radius and bigger mountains, bigger canyon. So you don't really have a good definition by that, by the planets and non-planets. Because you have these purple things which are intermediate between the red things and the blue things. But if you look at the dynamic space definition, this is the inventory of the terrestrial planets, the Jovian planets. You have near-Earth asteroids are small, the main belt asteroids are small, Kuiper Belt objects are small, Centaur is even smaller, but they're closer in, and they're just fewer because they're crossing planets' orbits, so they don't last very long. And really, there's a big difference between these bodies and these bodies. I don't know if we'd call them the same thing. Yeah, they're all classified as planets. But I think if you took away Mercury, well, then do you take away Mars? People would get upset if you demoted Earth or something like that, even though some people just say, oh, there are only real 4 planets. But just kind of tradition, whereas there is a big gap in our solar system. It's probably not universal. It's just classifying things to make it a little bit easier to understand. With stars, there really is a difference, because stars, the definition is their self-sustained fusion. Let me tell you a little more about some of the small bodies. Okay. This, let's see, we did this before. Let's see if we can get it to work again. There's something, okay, yeah, there's something in here. Okay, yeah. Go back and reopen it, and then I'll open it on that side and just go on. And I'm just going to skip over that. I guess there's one problem slide.
Which one is it?
No, I didn't get that far. Let's see. So I can do it. Okay. Let me skip over that one and go to this. Okay. These are a couple of comets, nicely photographed comets. There's the nucleus, where most of the mass is, and then the material coming off in the coma and tail, and that's what you see at a great distance, except when it's really cold, and then there's nothing that's coming off. Because what's going on is the sun is vaporizing some of the ice, water ice, and some more volatile ices. And it's ice intermixed with dust. When the ice goes away, when it's vaporized, it's very low gravity, so it escapes. And it takes the dust with it, pulls the dust because the gravity is very little. So it escapes. In the case over here, you see actually two tails. You see the dust tail, but also an ion tail. And this is pointed out directly to the sun. You have ionized particles, and they are pushed away directly by the solar wind. Here's Comet Halley. This is actually a photograph taken in 1910 when it was a good apparition, easily seen from Earth. In 1986, this is a close-up from European Giotto spacecraft. Very dark, but this is an area where dust is coming off, very irregularly shaped. This is a picture of a less well-known comet, Built 2, high resolution, different, more round. Doesn't have to be irregularly shaped just because it's small. It just can be. You can have a ball, round ball, you can have a billiard ball, or you can have something quite irregular, very easily. Gravity doesn't matter. Almost a decade ago, NASA sent a spacecraft to smash in to a comet. And it wasn't because we wanted to destroy a comet or anything. We wanted to see what was inside. And flew out, hit the comet. There were two spacecraft, an impactor and a mothership. The impactor took a few little photos close up on its way in, but this was the mothership and observing the comet before the impact, right after the impact, and all the debris, and it studied the spectrum of the debris, etc. They're all studied from Earth also to get more information on how comets interact with things, how much material, when it knocked material off, but it also exposed fresh ices from deep down, and how long it brightened for. It's the impact site. how it looked 45 minutes after the impact. That was one study. Now, just recently, Europeans have sent a spacecraft actually into orbit around a comet. This is the Rosetta mission. Gorgeous image. Very irregularly shaped. A little bit reminiscent in shape of Halley, but not in detail, certainly. All these little peaks, and they're going to actually send a small lander, and they're following this comet. So this is actually probably the most exciting thing in solar system science at the moment. And Rosetta mission, because it's just so new. All the other observations of comets have been from the ground or Earth orbit or from very fast flyby spacecraft, that one impact. But the in situ detail is just enormous, and we're going to learn a lot more about comets.
What is the size of the body?
That size is several kilometers. I'm not sure the exact amount. Does anybody know? It's the size of a city. Planets in our solar system. It's another view showing masses, radii, volumes, densities. Jupiter is really dominant. Saturn next, and then smaller ones, and then the really small ones, and Pluto, little guy. Now planets, the giant planets are really giants when compared to the terrestrial planets. But the sun, star, really, it's a very different type object. In composition, it's more than 98% hydrogen and helium. Jupiter's about 90%, Saturn's about 75%. But this body, self-luminous. Now, these bodies are somewhat self-luminous. They're radiating about twice as much energy as they absorb from the sun because they're still cooling off from their heat of from the formation. But the sun is about 10 billion times as luminous as Jupiter. And it's 1,000 times as massive, but 10 billion times more luminous. And that's because it's not getting energy just from contraction, it's getting energy from thermonuclear fusion. This is the spectrum, pretty much a black body. At short wavelengths, black bodies drop off substantially, exponential decrease. So small amounts of energy radiating in the upper atmosphere by accelerated charged particles start to dominate, but that's still very low compared to the intensity. I mean, a millionth the intensity in X-rays compared to visible light. This high energy in visible light is pretty uniform, the sun. Sometimes you see major sunspots, but in higher energy, you have much more variability, X-rays. Now, when we talk about astrobiology, we're also interested in how the sun changes with time. And the most important thing is how its luminosity changes. The sun is about 4.57 billion years old. And it's gradually increasing in luminosity. About 4 billion years ago, there's about 25% lower luminosity. It's gradually increasing. Things are going to get real unpleasant in a billion or so, billion to 2 billion years on Earth, well before it becomes a red giant. It's really hot for short periods of time, burns up its fuel, and then gets cold for very, very much longer time. if the universe sticks around. Let's put a magnifying glass here, and we see, well, it'll be twice the end of its main sequence, about twice now. It'll get up to a couple thousand, and then more like 3,000 times briefly. And intermediate between them, it'll be about 40 times its current luminosity. And that means farther out, there'll be enough radiation to have liquid water on the surface of bodies. And if you look at how long bodies can have water on their surfaces, well, it's real nice at around 1 AU, or a little more than 1 AU. It's about close to 10 billion years or 5 billion years, depending on how close the amount of energy you need to the current one is to have liquid water. Europa will have it for maybe 100 million years, a couple 100 million years. That's that satellite which has water, ice layer on top, but liquid water ocean below, tides. There are various types of stars. The astronomers will be very familiar with this, and I know, but this is just the temperature, type of radiation versus luminosity, depending on the mass of the star for the common ones. I don't want to explain in all details, but there are different types of stars. Don't want to spend 20 minutes on things that some people know, and I would need 20 minutes to explain to others, because it's not that crucial, really. But they're much smaller stars where you can see planets more easily around them. They're much cooler, so you need to be very close to them to be at a distance. It's like a cool ember. You need to be close to the fire to be warm enough. Okay, that's my presentation on solar system and stars. So I'd like to take a little period now. How far into my session are we? Oh, I want to break for questions. 20 minutes left? Okay. So I'll open things up for questions for maybe 5 to 10 minutes, see how things go. And if we have some time at the end, then I'm going to just start my planet formation lecture.
Let's thank Jack first.